So I'll start with a quick recap of the concept of chain rule in differentiation that we discussed last time. Then we'll come to questions and doubts. So this was used for differentiation of composite functions. Let's take a relook at it. So a composite function, as you know, is a function of this type, a function of a function. This is an example of a composite function. For example, if we have the function natural log of sin x, this is an example of a composite function, as you can see. Okay. So how this is a composite function is because on x we first operate g, get gx, and on that we operate f, to get f of gx. So in this example, you can see that on x we have first operated the sine function to get sin x, and then on that we have operated the natural log function to get natural log of sin x. So this is the operation of the g, you can say. Okay. So this is our gx, and this is the operation of f. So this is f of gx. So that's why this is a composite function. Okay. So for differentiation of composite function by chain rule, we saw that there are 3 steps. Substitution step. So in that we substitute a dummy variable as the inside function. So if I apply that step over here, in this particular case, I would take z as sin x. So immediately y becomes ln of z. Okay. Y becomes f of z. Then you have the second step, which is the chain rule itself. So this establishes that the rate of change of y with respect to x is equal to the rate of change of y with respect to z multiplied with dz by dx. So that will become f prime of z on substituting y as fz multiplied with g prime of x. So in this case, when we apply the second step, you would see that differentiation of y with respect to z, that will become 1 by z, and differentiation of z with respect to x, that will become cos x. And the final step, the resubstitution. So replace z with gx. So this is what we get. So here, when we do the resubstitution, z will be substituted as sin x. So this will become 1 by sin x into cos x. Or in this case, we can say that dy by dx would be cot x. That would become my final answer. Okay, so hope the method is clear to all of you, which we have seen on the left hand side, and the particular example on which we have applied the method, which is on the right hand side. Hope this is also clear. Okay, so let's do an example question next. Okay, just find dy by dx here. Work it out quickly and send me the answers on the text message. Okay, very good. Let's check out the answers. Pratyush, Shivesh, Saurabh, correct answers. Sayan, Ishita, also correct. Aryan, Prathmesh, Adinath, correct answers. Anand Mishra, correct. Okay, so let's understand this is a chain, this is a composite function, because what we do to get y is on x, we first operate the quadratic function, which gives us x square plus 2x. So this is our, you can say, g x, and on that we operate the sine function. So that is our f of gx to get sine of this quadratic function x square plus 2x. Okay. So the substitution step that we'll do here is that we'll take z as, or you can call it any other variable, but a new variable, the dummy variable is x square plus 2x. So y becomes sine z. So then our chain rule step becomes derivative of y with respect to z into derivative of z with respect to x. So differentiation of sine z, you can see, is cos z, and differentiation of x square plus 2x is 2x plus 2. So now just the resubstitution will tell us that dy by dx is 2x plus 2 into cos of z, where z is again x square plus 2x. So this can be left as the answer, or you can further just take the two common.
Sir, how did we get 2x plus 2? Can you explain, please?
Yes, it is coming from substitution. Okay. So you can see that this quantity dz by dx, okay, that is the differentiation of this. Okay. So that is differentiation of x square plus differentiation of 2x. So by formula, differentiation of x square is 2x. Differentiation of x is 1. Got it? No?
Yes, sir.
So substitute this dz by dx. Similarly, this one, dy by dz, is the differentiation with respect to z of sine z. So that by formula is cos z. So this is substituted here, and this one is substituted here.
Thank you, sir.
Okay. All right. Any other doubts? Hope this question is clear. Otherwise, to everyone.
Sir, just a silly doubt.
No problem.
Is cos x square and cos square x the same?
Okay, no, they are not the same in the sense that cos x square is basically, the more proper way of writing it is cos of x square. So if I have written a function like this, then for example, at x equal to, let's say, something, x equal to, let's say, pi by 4, the value of this function becomes cos of pi by 4 whole square. So that is cos of pi square by 16, whatever that value is in radians, I have to substitute. Okay. Whereas if you take a second function, cos square x, right? So that is nothing but actually cos x whole square. So this one's value at x equal to pi by 4 will become cos square pi by 4. Now cos pi by 4 we know is 1 by root 2. So that will be 1 by 2. So they are different things. Understood now?
Yes.
So what do we do when we have more than two functions?
We'll apply chain rule, but with more substituted variables. Okay, so that kind of question will just become more lengthy. So for example, we can have something like this. We could have y is equal to ln of sine of x square. So talking about this type of question, right?
Yes, sir.
So on x we've operated whole square first, so we've got x square. On that we've operated sine, so we've got sine of x square. And on that we've operated ln, so we've got ln of sine x square. Okay, so we just have to substitute more variables. So here the first step when we do substitution become like this, that let's say z is equal to x square, so y is equal to ln of sine z. So this is still a composite function. Okay, so what we'll have to do is another substitution. So let's take sine z as, let's say, another variable u. So now y becomes ln u. So you can see that z is x square, okay, and u is equal to sine z, okay, and y is finally ln u. So y is related to u itself is related to z, and z is related to x square. So this is our z, okay, this is our u, and finally this is our y, the above example. So now the chain rule step will just involve one more in between variable. So dy by dx, when we substitute, now we can see here that y is related to u. So this is dy by du. Okay, but then in turn u is related to z. So into du by dz. Okay, and in turn z is related to x. So we have dz by dx. Now we'll substitute each of these. Okay, so this is differentiation with respect to u of ln u into differentiation with respect to z of sine z into differentiation with respect to x of z, which is x square. So just one extra step comes in between, as you can see. So differentiation of ln u is 1 by u. This is cos z, okay, and this is 2x. Now when we do the resubstitution also, there is two steps. So first we'll substitute u as sine z. So this is 1 by sine z into cos z into 2x. So that is 2x cot z. And again we do resubstitution, that z is how much? It's x square. So this becomes 2x cot of x square. So this becomes finally our dy by dx. Okay, so this is a more lengthy type of question. Okay, it's a more extreme application of chain rule. But yes, if we have a double layered function instead of a single layered function, that a function of a function and then another function operated on it, so we can always use chain rule in a more extended manner like this. Okay, beta. So hope this answers your question.
Yes, sir.
Okay. Yes, Adinath and Anshul, very good. That's correct. Yes, Parv, you have a question, beta? Please ask.
Yes, sir. Won't we substitute the sine z and make okay?
Sorry, won't we substitute?
The sine z. I thought you had written cos z over there instead of cot.
हाँ, okay. Understood ना? So u
Yes.
को मैंने क्या substitute किया पहले? Sin z. फिर बाद में z को क्या substitute कर दिया? x.
X.
So first this step, cos z by sin z became cot z here, and in this we substituted z finally as what? X. So that's how we got the answer.
Yes, sir. Got it.
Right? It's clear now? Okay. Okay. Now next, let's spend some time with any questions and doubts in the assignments. Okay. So you finished writing this down or going through this. Let's come to doubts and discussions from the assignments. Yeah, Ishita, you have any doubt?
Yes, sir. Y is equal to root x multiplied by 1 plus x squared to the power 3 by 2.
Okay, we'll discuss that. Y is equal to, what was it? Root x multiplied with
1 plus x squared
uh,
whole to
the
the power 3 by 2.
whole to the power 3 by 2. Okay. Okay, so what we'll have to do in this type of question, I'll explain. Let's do this as a doubt, okay? We'll have to use product rule because this is multiplied by this, and the second function that we have got, that itself is a composite function because it is a quadratic function 1 plus x square raised to some power, that is 3 by 2. Understood now?
Yes, sir.
So I'll explain how to do this. Okay. So after doing this question, if anybody has a doubt in assignment 1 and 2, Parv, your doubt is cleared, beta?
Yes, sir.
Okay. Yeah. So if anybody has a doubt in, okay, I've received a couple of doubts, Adinath and Akshat, from assignment 3 and also from the module. But we'll, after this question that I'm doing, this one here, I'm going to go systematically. So if anybody has doubts in assignment 1 and 2, we can first discuss those. Okay, then we'll come to assignment 3 and the module. Okay. So anyhow, let's work out this question. So in this question, what we can do is to make the whole thing look simpler. Okay. You can write this as fx into gx. Okay, where fx is the simple function root x, but gx is the composite function 1 plus x squared to the power 3 by 2. Okay. So gx, you can see, is that type of function. It is, let's say, h of kx, where h is the power 3 by 2 function and kx is the quadratic function 1 plus x squared. So anyway, so once we have written this as a product, you can see that dy by dx will become f prime of x into gx plus fx into g prime x. Okay. So f prime is very simple over here. From this, we can see that fx is root x. So derivative of f is 1 by 2 root x. So the first one is quite simply done. But what about g prime? So we'll have to understand that separately from this. So gx is 1 plus x squared to the power 3 by 2. So g prime x is how much now? So for that, we'll have to use chain rule. What we'll have to do here is substitute 1 plus x square as z. So gx is z to the power 3 by 2. Okay. So differentiation of gx with respect to x will become differentiation of z to the power 3 by 2 with respect to z into differentiation of 1 plus x square with respect to x. So that becomes 3 by 2 root z into 2x. So that becomes 3x root z, which is this. So this is our g prime x. So now we go back to the original function and substitute in the derivative. We substitute this. Okay. So going back to this now, it becomes f prime of gx. So f prime is 1 by 2 root x into gx was this function. Okay. Plus fx, which was root x, into g prime x, which is now this function. So that makes it 1 plus x squared to the power 3 by 2 divided by 2 root x, right, plus 3x root x into 1 plus x squared to the power half. We can write it like this, divided by, sorry, just that much. Okay. So then we can simplify this a bit further also. We can take 1 plus x square to the power half common. So this becomes 1 plus x square upon 2 root x, okay, plus 3x root x. And further we can take LCM in this and all that also. So become 1 plus x square plus 6x square. Right? So our final answer will become something like this. So Ishita, the method is clear, I hope.
Yes, sir.
Okay. So just go through this once and also note down the key steps if required. Okay. Now let's come to assignment 1 if there are any doubts, or worksheet 1 which I had given. Okay. So question number 2, Anshul has asked. Okay. Also Prathamesh. Anand, to answer your question in this, we will not be able to apply chain rule directly, no? Because we cannot make any type of substitution here, which will express y directly as a composite function. It is a product of a composite function with another function root x. Okay, so from assignment 1, we are going to be discussing question number 2 and also Anshul has asked question 1E part. Okay, so let's go through that next. Okay, so I'm just going to share the assignment 1 questions once. Okay, so question 1, the part E, let's go through this once. Average speed in the last 10 seconds. Okay. So best way to understand this was to first understand it in terms of graph of speed versus time. What was happening in the graph of speed versus time here was that the motion was starting from rest at time t equal to 0. Okay. So it started from rest. So initial velocity was 0 from t equal to 0 with a uniformly increasing speed at the rate of 2 meters per second square. So the acceleration is 2 meters per second square, but for 10 seconds. So let's say this is how that part of the graph goes. So at 10 seconds, having an acceleration of 2 meters per second square, you can see that the velocity would have reached a into t. So that is 20 meters per second. And then thereafter, what is happening? It is decelerating at the rate of 4 meters per second square. So from that, we'd understand for the speed to come from 20 meters per second to 0 at the acceleration of minus 4 meters per second square, we can see the time taken would be equal to 20 by 4 or 5 seconds. So the second part of the graph would have been like this. At 15 seconds, it would have come to rest because this part had an acceleration of plus 2. This part had a deceleration of 4. Okay. So this graph is clear. Anshul,
Yes, sir.
yeah, Anshul Tiwari, this graph is clear, no?
Yes, sir.
Okay, now see what we want to do is we want to find the average speed in the last 10 seconds. So which is the last 10 seconds here? This is the last 10 seconds from 5 seconds to 15 seconds. This is the cycle. This is the last 10 seconds. Okay. So we want to find the average velocity in these last 10 seconds. So that is from 5 to 15. We have to calculate the distance traveled from 5 to 15 and divide that by the time interval of 10 seconds. So what will be the easiest way of calculating the distance here? Since I've already made the graph, the easiest way of calculating the distance here would be this total area. Okay. So this can be calculated as the area from 5 to 15 divided by the time interval, which is 10 seconds. Now let's calculate the area. So to calculate that area, first let's look at this part of the graph, the one that is going from 0 to 10 seconds. In that, what is happening from 5 to 10 seconds? Let's understand that. So at 10 seconds, the velocity has become 20 meters per second. So obviously at half time of 5 seconds, the velocity would have been 10 meters per second. So this area, let's say this is A1. This area we can write as area of trapezium, half into sum of parallel sides into distance between them, that is 5 seconds. Okay. So this is in meters per second, this is in seconds. So this area will come in meters. So 30 into 5 by 2, so that's 75 meters. So this is in fact the distance traveled. This is equal to the distance traveled from 5 to 10 seconds. Okay. And then we have the second thing, the distance traveled, let's say this triangle. So that A2 is the distance traveled from 10 to 15 seconds. So that is equal to how much? It is area of triangle. So half base, which is 5 seconds, into height, which is 20 meters per second. So that is becoming 50 meters. So the sum of these two areas here is 75 plus 50. So that is 125 divided by 10 seconds. Meters divided by seconds. So this should become 12.5. You understood now?
Yes, sir.
Okay, very good. Okay, Kevin and Ishita, we will discuss question number 4 also. Before that, let's do question number 2, which again a couple of people have asked. Okay, so I'm clearing this. Hope this is clear. Now let's come to the second question. So at this stage, with the amount of differentiation that we've learned, we can solve this question using rate of change and calculus also. But remember, back then when we had done this assignment, we had not really learned differentiation properly. Okay, so we are just going to solve this by the concept of ratio and proportion because the rate of change was uniform. Okay, so anyway, let's see what all information is given in the question. So the first information given that the base area of the tank is 50 centimeters square. It's a cylindrical tank, and initially the tank was empty, and now an inlet tap is opened to fill water at a uniform rate of 4 centimeter cube per second. So you can see the unit is in centimeter cube per second. So this is a volume rate. Okay. So we will take the volume of water in the tank as a function of time. Volume is changing with respect to time in such a way that t equal to 0, the volume was 0. Okay. But then then itself we started an inlet tap. Okay, so the inlet was letting water in at the rate. Now we'll write this as delta V by delta T. We can write it as dV by dt also. So that rate is how much? It is equal to 4 cc per second. Okay, and only the inlet is working. Okay, for the first 2 minutes. Okay. So up to t equal to, so if I take a general time now, okay, but this time is less than 120 seconds. So what is happening is at this particular time, the volume will become how much? It will become the inlet rate, that is 4 cubic centimeters per second multiplied by whatever t in seconds. So the volume of water in the tank is 4t cc. Okay. And therefore, if the height of the water column is h and the base area is a, so this volume is also equal to h into a. So this volume, which is 4t in cubic centimeters, is that height multiplied by 50 centimeters square. So you can see that the height is equal to 4 by 50 t, or we can write that as 0.08 t as a function of time. Okay. So to answer the first question, first part, calculate the volume of the tank and the rate at which the level or the height is changing at the time t equal to 1 minute. You can see t equal to 1 minute is coming in this category. So the volume of water at t equal to 60 seconds or 1 minute will come from this formula, 4 into 60. So that is 240 cubic centimeters. And now from this we will see that height is 0.08 t. So what about the rate of change of height? Delta h by delta t is equal to what? It is plus 0.08 centimeters per second. Because if you, from this, if you visualize the graph of height versus time, you can see the graph of height versus time is a straight line graph. Okay. So this straight line graph, h is equal to 0.08 t. It has a slope of 0.08. No? So that is the rate of change of height. So that is why at that point of time, which is t equal to 1 minute, the rate of change is plus 0.08 centimeters per second. Okay. So hope this part is clear. So Anshul and Pratmesh, hope this part of the question is clear to both of you. Now let's come to the next thing. What is happening? That after 2 minutes, the tank develops a leakage at the base where water leaks out at the rate of 8 centimeter cube per second. Okay. So I'm just going to switch to my whiteboard. Right. So what was happening here is from 0 to 2 minutes, there was only water coming through the inlet. There was no leakage. So the level of water was going up. So during this time, we saw that delta V by delta T was the rate of inlet, which was plus 4 cc per second. Okay. So from 0 to t, we see the volume of water in the tank, it was equal to 40 cubic centimeters. So the visualize the graph of volume versus time. You can see that for the first 2 minutes, the volume would have been increasing at the uniform rate till it reaches this value of 240 cc. Sorry, 480 cc. Reaches this value of 480 cc. Okay. Then what happens for t greater than 2 minutes, there is a leakage that develops. So that leakage is happening at the rate of 8 cc per second. While simultaneously the inlet is still there. Okay, so at this point of time, the inlet is letting in water, but at the same time there is some leakage here, let's say. So water continues to come in at the rate of 4 cc per second, but it also leaks out. So what will be happening now? The leakage is at a larger rate. The leakage is at 8 cc per second. So the leakage is dominating over the inlet. So the level of water will now start decreasing. Whereas here the level of water was increasing. So we saw that the height was equal to volume divided by area. So that was as a function of time. So if we simultaneously also look at the height with respect to time, you can see in the first part of the motion of the system, 2 minutes, the height was increasing. Okay. And the height would have reached 480 divided by 50 centimeters square. So 480 divided by 50 would have given us 48 by 5. So that is 9.6 centimeters. Okay. But now what is happening in the second part, the rate at which the volume is changing in this time, t greater than 2 minutes, okay, that is equal to +4 minus 8. So that is minus 4 cubic centimeters per second. Okay. So the volume is decreasing at this rate. So here it was increasing at the rate of +4, but now here it is decreasing at the rate of -4. So that means the volume will be changing like this with respect to time. Because it's falling at the same rate, so it will take the same amount of time to reach 0. So this should be 240 seconds when it becomes 0. This should be 240 seconds when the height again becomes 0. So the net rate of change of volume is negative. So this has a slope of minus 0.08. This has a slope of plus 0.08. Whereas similarly, this part here, this has a slope of +4, and this has a slope of -4, like this. Okay, so hope this part is clear also. Anshul and Prathamesh. Okay. So now going back to the question, the next thing that we've asked, the B part, calculate the level at 150 seconds and the rate at which the level is changing at this instant. So we have to calculate. Now 150 seconds is somewhere over here. So at 150 seconds, we have to calculate how much the height is. So let's look at that graph in more detail. So we see the level or the height of water in the tank as a function of time. You can see that that was first increasing for 20 seconds, sorry, 120 seconds. And then thereafter it was decreasing. So at 2 minutes or 120 seconds, it had reached the maximum height, which was 9.6 centimeters. Okay. But here it was increasing at the rate delta H by delta T was 0.08 centimeters per second. Okay, because remember the volume was increasing at the rate of 4 cubic centimeters per second. Okay, so the volume as a function of time was 4t. So the height as a function of time would have been volume by area. So that is 4t by 50 or 0.08t. This is what was happening from 0 to 120 seconds. Okay. Whereas from 120 to 240 seconds, the volume rate of change was equal to minus 4 cubic centimeters per second. So accordingly, the rate of change of height would have become minus of 0.08. Okay. So this slope here, delta H by delta T, is minus 0.08 centimeters per second. That is why when you reach here at 240 seconds, that is 4 minutes, the height finally becomes 0. So anyway, what we have to do now is we have to calculate the height at 150 seconds. So 150 is here. Okay. So you can see that this time interval is how much? It is 30 seconds. Okay. So in this 30 seconds, how much this would have dropped by? Okay. So delta H by delta T from 120 to 150 seconds is minus 0.08 centimeters per second. So this drop in height, which is occurring from 120 to 150 seconds, is equal to minus 0.08 multiplied by 30. Okay. So it is a drop of 2.4 centimeters from 120 to 150. Okay. So now you can correlate it and see that this value of height that we have, this was the unknown height at 150 seconds. So the height at 150 seconds is equal to the height at, let's say, 120 seconds plus the change in height from 120 to 150. You can write it like this. So that is equal to 9.6 minus 2.4. So that's how we had got this height as 7.2 centimeters at 150 seconds. Okay, so this hope is clear to all of you. Okay, so this is worksheet 1, question number 2's B part. Okay. And again, the rate at which the level is changing at this point of time is this rate. Okay. Okay, so that's the B part. Now let's come to the C part. What is the average rate of change of volume in the tank from 60 to 150 seconds? Okay. So I'll repeat the question. Average rate of change of volume with respect to time we have to calculate from 1 minute to 1.5 minutes. That is 60 seconds to 150 seconds. So this C part in the same question is the average rate of change of volume from 60 to 150 seconds. Okay, so we will define this average rate of change of volume as this. Okay. So it is the volume at 150 seconds minus the volume at 60 seconds divided by the time interval. So this is what we have to do. Okay. So instead of this H versus T graph, we will refer to the volume versus time graph, which has the same shape, but just that it's in terms of volume and time. Okay. So we've seen that the volume,
Sir,
yes.
sir, can you repeat what you just said? Because my laptop shut down, so I had to change my device.
Okay. So we are coming to the C part of the question, okay, which I've written down over here. You have to calculate the average rate of change of volume with respect to time from 60 to 150 seconds. Okay, this is what we are doing next. This is clear, now the B part.
Yes, sir. B part is clear.
Okay, so now C part, we have to calculate the average rate of change of volume from 60 seconds to 150 seconds. So we'll define average rate of change as this, the change in volume upon change in time. Okay. So is the final volume at 150 seconds minus the volume at 60 seconds divided by the time interval, which is this. Okay. So let's go back to the volume time graph to solve this. So in the volume time graph, we can see that the volume had gone from 0 to 480 cc in 120 seconds, and then again came back to 0 in this. Okay, so in this 60 seconds is somewhere over here, and at 60 seconds you can see that the volume would be exactly half of this 240 cc. Okay. Whereas 150 seconds is somewhere over here, and at 150 seconds we can see what this volume will be. Okay, so volume at 150 will be equal to volume at 120 plus change in volume from 120 to 150. So in this second part, you can see that the slope was how much? It was -4 cubic centimeters per second. Okay. So this change in volume will become -4 multiplied by 30 seconds. Okay. So there will be -120 cc. So volume at 150 is the volume at 120, which is 480 cc, plus this change, which is a drop of 120 cc. So this is 360 cc. So that's how we know that this volume here should be 360 cc. So now the average rate of change of volume with respect to time from 60 seconds to 150 seconds is equal to the volume at 150 minus the volume at 60 divided by the time interval. So this is 360 cc minus 240 cc divided by 90 seconds. That's 4 by 3 or 1.33. So this is the average rate from 60 to 150 seconds. Okay, so this is the last part of that question. Okay, now let's come to question 4 of assignment 1.
Sir,
Again, couple of students have asked that, so let's go through that. So question 4 is really all about understanding the graph. Okay, and there's no direct information given about the graph, so we have to just observe it from, we have to observe it directly from the shape given and understand it. So first of all, what graph it is, you can see it's a distance versus time graph. S versus T graph. So it's a distance time graph. So what we know about distance time graph is that slope is equal to speed. The slope of the graph is equal to speed. Now, when we look at the graph a little more closely, what we can observe. So let's magnify this. Okay, so what we can observe is that it appears to be having a uniform slope from this point to this point. This part appears to be having a uniform slope. So let's say this is A, this is B, and this is C. So A to B, you can see is a straight line. Okay. It has a slope of this thing, delta S by delta T. So that is so 20, and this is in meters, this is in second. So it has a uniform speed. So this part, it has a uniform speed, which is equal to this much. Okay, but at the same time, if you observe from 0 to A, what is happening? If the slope was like this here, by the time you come here, the slope is like this. By the time you come here, the slope is like this. So 0 to A, we have increasing slope. So that means from 0 to 10 seconds, it is accelerated motion. Whereas this was showing us that from 10 to 20 seconds, it is uniform motion. Okay. Now again, if you come to this part, you can see from B to C, the slope is decreasing. We draw tangents like this, so you can see we have decreasing slope. So that is showing us that from 20 to 30 seconds, we have decelerated motion. Okay. And finally, after C, so T greater than 30 seconds, it's at rest. Because the distance is not changing anymore. It's fixed. Okay, now, so understood this quality of the motion that you learn by just observing the graph. Right, so Kevin and Ishita, both of you have asked to discuss question number 4. So these points are clear about question number 4?
Yes, sir.
Yes, sir.
Very good. So now once these points are clear, you don't really have to do anything else much in the graph, in the question. You have to just correlate the answers from this. Okay. So is the motion decelerated in any interval? Yes. You can see it is decelerated from 20 to 30. Is the motion accelerated? Yes. It's from 0 to 10 seconds. Instantaneous speed at 15 seconds. Okay. Now you can see 15 is in that part of the graph, which is a straight line between 10 and 20. So you have that property that when you have uniform motion, the instantaneous speed at any moment is the same as the average speed, which we calculated was that 20 meters per second. Okay. And the last part.
Sir.
Yes.
The motion is accelerated from 0 to 20, I think. Can we say that?
Sorry, come again.
The motion is accelerated from 0 to 20. Can we say that?
No, we cannot say that, beta, because between 10 and 20, now you can see the slope is uniform. It's a straight line. It's
Yes,
only
sir.
between 0 and 10 that the graph is curving such that the slope is increasing. But then between 10 and 20, the slope is constant. So that means the speed is uniform. You understanding now?
Okay, sir.
This is a distance versus time graph, no? Not a speed versus time graph. So distance is increasing uniformly with respect to time between 10 and 20. So it's not having an accelerated motion then. But between 0 and 10, you can see that in equal intervals of time, it's covering more and more distance. You can also observe that by doing this kind of analysis, that you go with a more simple definition of what is accelerated motion and what is uniform motion or decelerated motion, just in terms of equal intervals of time. So you take equal intervals of time here, and you can see during those equal intervals of time, the distance is increasing like this. You can see that these gaps are becoming larger and larger. So in equal intervals of time, it's covering more and more distance. But similarly, in this part, in equal intervals of time, it's covering less and less distance. You can see that these will be decreasing. So, whereas here it is in equal intervals of time, it's covering equal distances, because it's having a uniform slope. So that's why you can understand that this part of the motion is uniform from here to here. This part of the motion is decelerated, and this part of the motion is accelerated. Okay, so hope this is clear. Okay, so this is all okay. Okay, now what is the instantaneous speed at 15 seconds? So you can see 15 seconds is in that part of the motion when it was uniform. So instantaneous speed at 15 will be equal to the average speed in this interval, because it's having the uniform motion there, which we saw is 20 meters per second. So the instantaneous speed at t equal to 15 seconds is that uniform speed that is occurring between 10 and 20. So it's 20 meters per second.
Sir,
So, yes.
so could you please tell what is the instantaneous speed at 16 at 25 seconds in deaccelerated motion?
16 भी same होगा, because 16 is part of this. Okay, but 25 we cannot tell, because we don't know the rate of deceleration. No? You understanding the point?
Yes, sir.
We don't know the rate of deceleration. If we make an assumption that it's a uniform deceleration, then we can predict, because we can see that the speed at 20 seconds is how much? It is 20 meters per second. And we can also see that by the time you reach 30, the speed is becoming how much? It's becoming 0, because it's becoming a flat line. So if we assume uniform deceleration, but that would be an assumption, because we don't know this curve right now. You're getting my point? So if we assume
sir.
uniform deceleration, then that deceleration would be how much? Is decreasing from 20 to 0 in 10 seconds. So it would be minus 2 meters per second square. So then we could say that, okay, at 25, how much the speed would have become? It would have become 20 minus 2 into 5. So it would have become 10 meters per second. But that we cannot tell as of now from the graph. Okay, is it clear, beta?
Yes, sir.
Okay. So that is why, see, in the question, I have not asked you to calculate instantaneous speed in any of these parts between 0 and 10 and 10, 20 and 30, because I have not given any indication that we can assume that A is uniform here and here. The only thing we can assume from the graph is that this part is a straight line. That is from the shape of the graph. That's the only thing we can assume. We don't know this shape, what it is. We don't know what this shape is. We don't know whether this is uniform deceleration and whether this is uniform acceleration. But we know that in this part, the acceleration is 0. We know in this part, the acceleration is something negative. It may be uniform, it may be non-uniform. Similarly, here it is something positive. It may or may not be uniform. Okay, now let's come to this part. What is the average speed from 10 to 30 seconds? Okay. So average speed, we'll just use the definition. Average speed is equal to total distance upon total time. Okay. So we are talking about 10 to 30 seconds. We are talking from this time to this time. So you can see the total distance is this. Okay. And the total time is this. Okay. So total distance is becoming how much? It's becoming 100 to 400. So 300 meters divided by the time interval 10 to 30. So that's 20 seconds. So it's 15 meters per second. That's the average speed. Okay. So if you see, this average speed is less than the average speed between 10 and 20, which was 20 meters per second, because in between somewhere is decelerating. Okay. Similarly, average speed from 0 to 40. Now 40 is not shown in the graph, but you can see that after 30 it stopped. So 0 to 40, the total distance is 400 meters only. Okay. So it's 400 meters covered in 40 seconds. So the average speed is 10 meters per second, even lesser than this. Okay, people, so hope this question is fully clear now.
Yes, sir.
Yes, sir.
Yes, sir.
So anything else in assignment 1, please let me know. Otherwise, we'll do a quick run through of assignment 2 before coming to assignment 3. Okay, so I'm assuming assignment 1 is clear to everybody now. Just give me a moment. We'll move on to assignment. We'll just go through assignment 2 once. Okay, so let's do a quick pass at assignment 2. So question 1, I hope if anybody has a doubt, please let me know. Any of the differentiations? Okay, question 2. Okay. Question 3, I think we discussed in a bit of detail anyway, but just let me know in case there's a doubt, particularly this third part, the equation of tangent drawn at the point x equal to 2. Okay. Now you remember that question 4, at this stage we had not learned chain rule or quotient rule or anything like that. So we had to actually simplify these and differentiate. But if you go back to this question now, you can actually do this in a different method. Instead of simplifying, you can, for example, use the quotient rule here in part A, or in part B, you can also use chain rule. You can take x square plus 1 is z. So y becomes z square. So you can take a relook at these questions and also solve them by the newer methods that you've learned after this. Okay. And question 5 also is, I hope, clear to all of you. I think we discussed in class also. All right, so let's come to assignment 3 then. So I'm assuming all this is clear. So assignment 3, I have, yeah, somebody has a doubt? Ayush? Yes, Ayush? Okay, Ayush, I'm not able to hear you. There's some disturbance at your end, I think. If you have a doubt, you can also text message me, okay, in case your microphone is not working. You can just text me. Okay, so let me come to assignment 3. Number of questions have been asked in that. Okay, wait a minute. Before this, Srijita has asked question number 2 of assignment 1A part. Okay, let's go back to that for a moment. Okay, so we have to calculate the rate at which the volume of water in the tank is changing in question 2A part. So going back to worksheet 1, question number 2A part. Okay. So this was what was happening from 0 to 2 minutes. In this interval of time, inlet pipe was letting in water at the rate of 4 cubic centimeters per second. Okay, and initially the volume of water in the tank was 0. So at some time t, the volume of water would have risen. I mean, the height would have risen to h. So volume will become how much? So this rate is 4 cc per second. You understanding this, Srijita? That water is coming in at the rate of 4 cubic centimeters every second. No?
Yes, sir.
So just use unitary method. In 1 second, 4 cubic centimeters is coming. So in t seconds, how much will come? 4 into t
Yes, sir.
cubic centimeters. Okay, where t is in seconds. So this is the volume at any point of time. So for example, okay, if we take t equal to 1 second, the volume will be 4 cc. If we take t equal to 10 seconds, the volume would have risen to 40 cc. If we have taken t equal to 60 seconds, that is 1 minute, by now the volume has increased to 240 cc, like this. So this is the situation right up to 2 minutes before the leakage happens. So we can visualize the volume is changing with respect to time, like this. It's increasing at the rate of 4 cc per second. So in 120 seconds, it increases all the way to 480 cubic centimeters. Okay. Now, if this height is h and the base area is a, so at the instant when volume is so much, we can also write that the volume is equal to height into area. Okay. So the height of liquid in the tank, that is equal to how much? It is
Volume upon area.
40 in cubic centimeters divided by 15 centimeters squared. So that is how we are getting the formula for height as 0.08 t in centimeters at time t in seconds. So now if we visualize the height versus time graph, that's also a straight line graph which has a slope of 0.08. So from 0 to 120 seconds, the height is changing from 0 to 9.6 centimeters. Just multiply this with 120. Okay. So now what is the rate at which the height is changing? The rate is nothing but the slope of this line. Okay. So at this point of time, the rate delta h by delta t is equal to the slope of this, which is 0.08 centimeters per second. Just like the rate at which the volume is changing is the slope of this, so that is 4 cc per second. This one has a slope of 0.08 centimeters per second. Okay, so Srijita, is it clear now?
Yes, sir.
Okay. All right, let's come to assignment 3 next. So I'm just going through the messages once again. Number of people have asked questions from assignment number 3. Amol has asked question 2D. Okay, so we'll come to that. Okay. Okay, so can we just go systematically? Anybody has a doubt in question 1 of assignment 3? Any part of question 1 in assignment 3? Do you have a doubt? No. Okay. Question 2. Okay, Srijita 1E. Okay, let's look at 1E first. Okay, so 1E is y is equal to e raised power sin x, and we have to find the value of the derivative at x equal to 0. Okay. So let me repeat the question. So y is equal to e raised power sin x, and we have to find the value of the derivative at the point x equal to 0. So in this, what we'll do is, first step, we'll find the derivative. Then we'll find its value. So what is the derivative? So we'll have to use chain rule. So we can take sin x as z. So y becomes e raised power z. Okay. So dy by dx is this. Okay. So dy by dz is the derivative of e raised power z, which is e raised power z only, whereas dz by dx is the derivative of sin x, which is cos x. Okay. And then resubstituting, we can see that dy by dx, or the derivative, is cos x into e raised power sin x. So this is the first thing, we've got the derivative. Now next thing is the value of the derivative at x equal to 0. So substitute x equal to 0 here. So it is cos 0 into e raised power sin 0. Now we know that cos 0 is equal to 1 and sin 0 is equal to 0. So that becomes 1 into e raised power 0, which will become 1, because we know
Sir?
that e. Yes.
Sir, the 0 given is in radians or in degrees?
It doesn't matter. No? 0 degrees is equal to 0 radians only.
Okay.
Yes, no? So that's why no unit was given. Okay. Actually, in any case, if no unit is given, the default meaning is radians. Okay. If I give some angle as, let's say, 1.73, so this will be, unless I've given degrees here, we'll assume it to be in radians. Okay. And pi radians is this much, because pi is an irrational number whose approximate value is 3.14 or 22 by 7. Yes, so Srijita, hope this is clear.
Yes, sir.
Okay. Any other doubt in this question? Question 1, any part?
Sir, sir, can we say the derivative of e sin x is e sin x itself?
No, the derivative of e raised power sin x is cos x into e raised power sin x better. You understood, na? Because derivative is with respect to x, na?
Okay, sir.
What's the point? So e raised power sin x is actually which thing? It is dy by dz. It is not dy by dx. This e raised power z is the derivative of e raised power z with respect to z. But z itself is sin x. Na?
Yes, sir.
So if y is written as a function of x like this, then the derivative of y is this thing. It is cos x into e raised power sin x. Okay. Now let's come to the second question. Just go through all the parts. Let me know if there's any doubt. Okay.
Sir,
So yes, tell me.
so what if it is given that find the value of the derivative at y equal to 0?
At y equal to 0, then you'll have to solve the value of x for which y is 0. So generally that the question will not be given in that form. But if it is given in that form, then you'll have to do this, that you'll have to, so going back to that question, if I ask you find the derivative of the function at the point at which y is 0, you'll have to solve for this first. Y is equal to 0 implies e raised by sin x is 0. This does not exist, okay, because sin x is between -1 and +1. So you can see that y's minimum value is e raised by -1, which is 1 by e, which is quite a bit greater than 0. So such a point does not exist only where y is becoming 0. You understanding better?
Yes, sir.
Okay. But suppose we had this function, we had y is equal to e raised by x, and we wanted to find dy by dx at the point where y is 0. So here you can see that y tends to 0 as x tends to -infinity. Okay. So the value of dy by dx would also be 0, no? Because derivative of e raised by x is e raised by x. So y is 0 means x is tending to -infinity. So that means dy by dx is also tending to 0. And that you can understand from the graph of the function. So like this, no? So at a point where y tends to 0, the graph is almost flat. So the slope of the tangent is also 0.
Okay, sir.
Okay, so let's just go over the questions from the assignment once. So second question, I think all of you are clear with. Okay. Now, unfortunately, there are two question number 3s. I made a mistake in the numbering. So the first of the two question 3s. Any doubt in this? Okay, Srijita, so we'll discuss question number 3.
You said the second 3.
Okay, so the function given to us is x to the power 4 minus 2x square.
Sir,
So these values, so okay, we can calculate, but more importantly, slope of the tangent at these various points. And from that, we have to draw an approximate graph. Okay. So if we take different values of x
Sir?
and calculate y, so for example, at x equal to -3, we can see the value of y will become, yes, Rijita?
sir, the second 3, not this one.
As a second thing, okay. So anyone else has a doubt in this one? Okay. Second one is like more or less, a straightforward question. So what is given to us is that y is square root of z and z is this. So it's like the relationship between y and x is given indirectly. Okay, like we actually break it up in a composite function. So here is given in broken up form only. Okay. So we connect these two, we can see that y is actually square root of this. This is the relationship we're looking for. Okay, from this. Okay. Okay, so that is our expression of y as a function of x.
Sir, I
Because
understood.
okay, so this is your y as a function of x. Now you want to find the value of y at x equal to 2. So you can see that is square root of 2 cube plus 3 into 2 square plus 2. So that becomes square root of 8 plus 12. That's 20 plus 2. So square root of 22. Okay. Then we want to find dy by dz.
Sir, I understood.
Sorry, what? Can you
I
speak?
understood.
I didn't get you better. Can you speak a bit louder?
Sir, I have understood this.
Acha, you understood. So you had a doubt in this B part or something?
Sir, only the A part.
Oh, only the A part. Okay. So the rest of the things are clear in this question?
Yes, sir.
Okay. All right. So few of you are asked question number 5. We'll come to that. But before that, any doubt in question number 4? Okay. In 4, unfortunately, there's a bit of a print issue. This thing here, this is actually 2 pi by 3 or 120 degrees. So again here, okay, so let's come to question number 5 then. Let's understand the question, then we'll solve it fully. So once again, see, the information given to us is that we have a cylinder which is initially empty. Okay. Now, gas is pumped into the cylinder at this rate. So this is the rate of pumping gas into the cylinder. Okay. But at the same time, there is also leakage. This is the rate of leakage. Okay. So first of all, what is the net rate at which the mass of gas is changing? So it will be the rate at, so let's say here what is happening is the mass of gas in the tank. It will be a function of time. Okay. It will be a function of time such that at t equal to 0, m is equal to 0, because initially it was empty. Okay. Now the rate at which this mass is changing, that is dm by dt. So logically what it should be the rate of pumping minus the rate of leakage Okay, this is a logical statement that I've written. Hope this is making sense. Okay. The rate at which mass changes is the rate at which we are pumping in the gas minus the rate at which the leakage is happening. It's like two things happening simultaneously. If we were only pumping, then mass would increase at the rate of pumping. If it was only leaking, then mass would decrease at the rate of the leakage. So when simultaneously pumping and leaking is happening, so the net rate of change will be equal to this quantity here. So from this now we can see that the rate of change of mass will be equal to the rate at which we are pumping, which is a variable rate, by the way, minus the rate at which it's leaking out, which is a constant rate. So it is equal to 2 plus T in grams per second. So what this means is that this is an instantaneous rate. For example, at T equal to 0, when the system starts, the net rate of change of mass is 2 grams per second. But by the time it's 1 second, it's increased to 3. By the time it's 5 seconds, it's increased to 7. By the time it's 10 seconds, it's increased to 12. So with time, the rate of change of mass is changing. Okay, so first of all, hope this point is clear to all of you, because this is what will help us solve the next part of the question. Okay. So once we have understood that the net rate of change of mass is this. Okay, so we have got that dm by dt is equal to 2 plus t in grams, where time is in seconds. Okay. Now also we had the information that mass was equal to 0 at t equal to 0. So we'll have to make use of this also for this part. What is the mass of the tank as a function of time? Mass of gas in the tank. So I know the rate of change of mass. Okay. Now if you look at the rate of change, you can see that this rate is linear with respect to time. Okay. So what we can say about the mass itself, it should be quadratic in time, because we know that rate of change of a quadratic function is a linear function. Okay. Because we know that if we take y is equal to ax square plus bx plus c, then dy by dx is 2ax plus b. So if this is linear, this has to be quadratic. We are using that quantity. We are using that relation. So let's assume that mass is some coefficient into t square plus some coefficient into t plus some constant. So now we have to find A, B, and C. So the first thing we'll bring in to find this is this fact. So m is equal to 0 at t equal to 0. So we can see that C is equal to 0. Okay. And then the second thing we'll bring in is this relation. We'll substitute this over here. So dm by dt, according to this, should be how much? Dm by dt should be the rate of change of at square plus b, because already, sorry, plus bt, because already we have seen that c is 0. So dm by dt is how much? It's equal to 2 plus t, and on the other side that should be equal to 2at plus b. So when I compare both sides of the equation, the coefficient of t is how much? 1 on this side, so that means a is 0.5, and the constant quantity is b on that side. On this side, it's how much? It's 2. So b is equal to, and already we had c is equal to 0. So now using this, we come back to this. What is m? It is 0.5 t square, that is 80 square, plus bt, so that is 2t plus c, which is 0. So this is the mass as a function of time.
Sir, how did you get A and B's value from
By
that
comparing
equation?
both sides of the equation, no? Dm by dt is 2 plus t, so that's equal to 2at plus b. No? Okay, so the coefficient of t on both sides of the equation, on left hand side it is 1, on the right hand side it is 2a. So 2a is equal to 1, and the constant term 2 should be equal to on the other side b, so b is equal to 2. Okay, so hope this is clear, people.
Yes, sir.
Okay. So now once I've got this function of time, I can easily take some values and plot the graph. Okay. So this part I want to do now. Approximate graph of mass versus time from 0 to 30 seconds. So we saw mass versus time. Is like this. Okay. So we just take some values. So for example, at t equal to 1 second, we can see the mass is 2.5 grams. Okay. At t equal to, for example, 5 seconds, we can see it is 10 plus 12.5. So that will be 22.5 grams. At t equal to 10 seconds, for example, it will be 20 plus 50. So it will be 70 grams. At t equal to 20 seconds, for example, it will become 40 plus 200. So 240 grams. And at t equal to 30 seconds, you'll see it will be 60 plus 450. Okay, so that's 510 grams. So if you just kind of draw an approximate graph, you can see how rapidly it's rising. As a non-linear kind of shape, it rises very rapidly from these values. Okay, so hope this question is clear to all of you now. All right, let's switch over to the module exercises. So I have received some requests, like Akshat has asked for question 25 and 26 from exercise 1. So let's start with that. So I think exercise 1 is on page 38 or something. Okay, also 19 and 26. Okay, so let's start with these questions. Rashmika, this is exercise 1 only, right?
Yes, sir.
Okay, so let's come to the module exercise 1. So we'll start with a couple of questions, 19, then 26, and also 25. Okay. Okay, Adinath will come to that also eventually. So just go over these questions. I'll discuss in a moment. Okay, so 19th question will be an example of chain rule again. Okay. So we have to find dy by dx for y being 1 by 4 tan to the power 4x. So we'll directly use the composite function method over here. We'll first substitute so y becomes very simple. It is z to the power 4 by 4. So next step, chain rule. So dy by dx will become derivative of this thing. So that is 1 by 4 into 4z cube into differentiation of z with respect to x, which by formula you know is sec square x. Okay. So now you have to just resubstitute. So dy by dx is z cube, which is tan cube x into sec square x. So you can leave the answer this way, or you can also simplify it further. You can write it as sine cube x upon cos cube into cos to the power 2. So that's cos to the power 5x. Or you can also write it as sine cube x into sec to the power 5x. So these are the different ways in which you can write it. Or you can also use the relation that 1 plus tan square x is equal to sec square x. You can also write it as tan cube x into 1 plus tan square x. Okay, right. So Amol has asked for question number 20 also. So let's quickly look at that.
Sir, I have applied the quotient rule here. Is that okay?
Sorry, what? I didn't get you better. Can you speak a little louder?
Sir, I have applied the quotient rule here. I mean, I have taken out the derivative for tan raised to 4x and then I have applied the quotient rule.
Which question you're talking about, beta?
19th,
Achha,
sir.
this one 19. What you have done? You have taken
Taken out the derivative of tan 4x, tan raised to 4x, just for that particular term and then did the quotient rule.
Didn't understand you better. What you've done?
Sir, I have taken out the derivative of tan raised to 4x first
Huh.
and then directly proceeded for the quotient rule.
Directly done what for the question?
Quotient rule, sir. Quotient rule, like the product rule, the quotient rule.
Quotient rule. अच्छा, sin
Yes,
to the
sir.
power 4 divided by cos to the power 4. वैसे करके किया आपने?
हाँ, sir.
But then it will become very lengthy, na beta, because the numerator is sin to the power 4. So again, for that also you have to use chain rule. The denominator is cos to the power 4. So for that also you have to use chain rule, no? You understanding? Just be a very lengthy way of solving the question. No? If you express
Okay,
this
sir.
as 1 by 4 into sin to the power 4x divided by cos to the power 4x. So your numerator is sin to the power 4. Your denominator is cos to the power 4. So when you use this method, that differentiation is denominator in differential of numerator minus this divided by denominator square. So for the numerator's derivative itself, you have to use chain rule, no? Because the numerator
Yes,
you
sir.
will write as z to the power 4, where z is equal to sin x. Then separately for the denominator, you will take as z to the power 4, where z is equal. So it will become very lengthy way of solving it. You're getting my point?
Yes, sir. I'm getting the point.
Okay, so you can avoid this method over here. Because there's no need to do it
Okay,
this way.
sir.
We know tan x's derivative is sec square x. Huh? So we don't need to break tan x as sin by cos. So hope the point is clear. Okay, so let's come to 20th question. So y is cos x minus 1 by 3 cos cube x. Okay, so dy by dx will become derivative of cos x minus 1 by 3 times derivative of cos cube x. Okay. So this we can write directly as minus sin x. But this term we'll have to separately differentiate. Okay. So let's take z as cos cube x. Okay. So therefore we can write so therefore differentiation of cos cube x can write like this, that it is dz by du into du by dx. So to differentiate this, we are using the chain rule method. So dz by du will become 3u square into du by dx will become minus sin x. Okay. So ultimately, this differentiation will become minus 3 sin x into u square. Now u was cos x, so cos square x. So this thing will now substitute over here. So further we can simplify it and write it like this. Now further we can simplify this and we can see that 1 minus cos square x is sin square x. So this is in fact minus sin cube x. So here I'm just using the substitution. Okay, let's move over to 25th question next. Twenty-fifth and 26th both, and actually 27th also, all three we have to solve. So let's look at this. So 25th question, we have y is equal to ln square of x. Okay, that basically means that it is ln x's whole square. That is the meaning of ln square x. Okay, so it's very simple. You take ln x as z, so y becomes z square. This can be a substitution step, and then chain rule. So this will become 2z into 1 by x. Okay. So this should become our answer. In contrast to this, you can see that the 26th question is y is equal to ln of x square. So better way to write it is x square is in the bracket. So ln is applied to the quantity x square. Okay. So now actually we have a couple of options in this. We can use chain rule, but there's no need to use chain rule. We can use the property of log, that log of anything to the power n is equal to n times log of that quantity. This is a property of log. So that means we can say that y is equal to 2 ln x. Then we can differentiate this directly. It's 2 times differentiation of ln x. So that is 2 by x. So this way we can avoid doing anything complicated, because it's reduced to a simple function by using this property that ln x square is 2 times ln x. So this property is coming from here. Or alternately, if you don't want to use this property, it will be a little more lengthy, but you can still do it by chain rule. Take x square as z. So y becomes ln z. So dy by dx becomes one by z into 2x. That is 1 by x square into 2x. That is 2 by x. You can see that this is the same as this. Okay, but this was totally unnecessary here, because you could have just reduced it to a simple function using the property of ln. So this is also clear to all of you. And let's also discuss 27th question. So here we'll have to use chain rule. Okay, so we will express ln x as z. So y becomes root z. So dy by dx becomes differentiation of root z, that is 1 by 2 root z, into differentiation of ln x, which is 1 by x. Okay, so that's the 27th one. Now let's come to exercise 3, question number 1, which Adinath has asked. So this is an important type of question set that we have in exercise 3, where we'll be using differentiation or calculus to solve practical physics type of problems. So it's all about how we set up the function and then find its derivative. Okay, so these questions are all pretty similar in exercise 3. So I'll just explain the first one, then you can try out the other ones yourself also. So it's saying that we have a circular disk which is being heated and its radius is increasing at a constant rate which is given to us. So we have to find the rate at which its area is increasing, right? So we have a disk like this, which is having some radius, let's say r, at some instant of time t. Now after a little while, because we are heating it, the radius is increased. So it's become a larger disk. Okay. So let's say now the radius is increased to r plus dr at time t plus dt. Okay. So you can see the area is increased by this much. So you can see that radius is some kind of function of time. It's increasing with time. Okay. Such that it's given in the question that the rate at which the radius is increasing is equal to whatever, half a millimeter, so 0.05 centimeters per second. This is what was given to us, that the radius increases at the rate of this much. Okay. So now from this we have to find the rate of change of the area at the instant when the radius's value is 3.2 centimeters. So what we have to do here is we have to understand in the question that area is some function of radius and radius is some kind of function of time. So rate of change of area with respect to time will be rate of change of area with respect to radius into dr by dt. So this is the practical application of chain rule over here. This is how we are practically going to apply chain rule to solve this problem. So from geometry we know that area is equal to pi r square. So now applying chain rule, should be this. So 2 pi r into dr by dt. Now we'll substitute these values. We want to find out the rate of change of area at the instant when r is 3.2 centimeters. As given to us that rate of change of r is so much. So substituting these, we can see that dA by dt at the instant when r is equal to 3.2 centimeters and the radius is changing at this rate. So that will become in centimeters square per second. This is at the instant when r is equal to 3.2 centimeters. So this exercise 3 is very important in learning how to solve an actual physical situation or a physics problem using the concept of chain rule, that one thing depends on another and the other depends on time. So how to find the rate of change of the first thing with respect to time. So here area depends on radius and radius is changing with time. So what is the relationship of how area is changing with respect to time? So that is a matter of the application of chain rule. Okay. So go over this solution carefully, and I will be giving you more assignment work also, plus you will be completing these exercises. So exercise 3, you can complete yourself now using this kind of concept. Okay, try out the other questions also. If there are more doubts while you are solving before next week's lecture, you can keep sending me the doubts on WhatsApp. I will give you some hints, okay, before we come to the doubt session on Sunday, or again the next lecture next week. So that's it for today, people. Hope you understood all this properly. Thanks for attending and wish you all the best.
Thank you, sir. Bye, sir.
Okay, people. Bye.